Hello dear students, we are back again with another video lesson. In a previous lesson, we finished with chapter 4. Today's lesson, we are going to explain chapter 5 about the magnetism. Today's lesson, we are diving into the fascinating world of the magnetism, and one of the fundamental forces of the nature plays a crucial roles in our daily life and advanced technologies. Magnetism is all around us, from the Earth's magnetic field to the devices that we use every day. So today's lesson we will explore the magnetism and the magnetic field and magnetic fluxes. Before starting lesson, I would like to give you some brief about this chapter. In chapter 5 about the magnetism, we have 3 sections. Section 1 about the magnetic field and magnetic fluxes. In section 2 we have 2 topics: magnetism from electricity. The first topic is about the magnetic field of current carrying wire and magnetic field of current loop, like circle and solenoid. In section 3, we will focus on the magnetic force, charged particles in magnetic field, and magnetic force on a current carrying conductor. Let's get started. In section 1, magnetic field and magnetic fluxes. At the end of this lesson, you will be able to understand what is the magnetic field lines and what is the magnetic fluxes. So the magnetic flux is very important to understand easy about the Michael Faraday in chapter 6. So chapter 5 is related with the chapter 6. Okay, we have some properties about the magnetism. As you know, each magnet has a north pole and a south pole. The minimum number of poles is 2 poles, north pole and south pole. Every magnetism in our world consists of 2 poles, north pole and south pole. Like poles repel each other and unlike poles attract each other. You have learned it in the other grades about the attraction and repulsion between 2 objects, 2 magnetic materials, magnetism with the magnetic materials. The 2 poles of magnetism, if they have the same pole, they will repel each other. Like north-north repel each other, south-south repel each other. So the like poles always repel each other because of the magnetic field lines. And the opposite poles like north and south, they attract each other. So I will tell you why the north pole and south pole attract each other, because of the field line. I will explain in detail. A magnet can magnetize other materials like iron and cobalt, call it the magnetic materials. Magnetism cannot magnetize every material. The magnetism can magnetize some material that call it the magnetic material like iron and cobalt. The minimum number of poles for magnet is 2 poles. If each magnet is divided into 2 pieces, each piece will have 2 poles, but 1 pole will be added to each pieces. For example, if you have a magnetism, north pole and south pole, if you make this magnetism into 2 pieces, okay, if you make the same magnetism into how many pieces? 2 pieces, okay? Each piece has north and south pole, okay? Each piece has what? Has north and south pole. But if the question asks is how many poles added to each piece? 1 pole, because already we have north pole in this side. Only the south pole is added for this north pole. And in this side we have a south pole, but north pole is added for this south pole. So finally we can say if you make a bar magnet into 2 pieces, each piece has 2 poles, but each piece 1 pole added for each piece. Okay, how many poles added for each of them when we make a magnetism into 2 pieces? You have to say 1 piece added for each of them. But if the question says how many poles does each piece have, you have to say each piece has 2 poles. In fact, no matter how many times permanent magnet is cut, each piece always has a north pole and south pole, as you can see in this figure. Look, this magnetism, this bar magnet is cut into many pieces, okay? Each piece always have north pole and south pole. Guys, we have 2 different types of the magnetic field. Earth's magnetic field, we have 2 poles, 2 different types of pole. The geographic pole of Earth and magnetic pole of Earth. The geographic north pole of Earth corresponds to what? To the magnetic south pole. And the geographic south pole of Earth corresponds to what? To the magnetic north pole. For example, assume that this is Earth. Okay? In the Earth, we have both magnetic pole and geographic pole. If this pole is the north pole of geographic, north of what? Geographic. So this pole becomes what? The south pole of Earth's magnetic field. South, sorry. This south is what? Earth's magnetic field. Earth's magnetic pole, sorry. Earth's magnetic pole. So the geographic north pole of Earth corresponding to what? Earth's magnetic pole. The south of Earth's magnetic pole. And the south of geographic pole, this is geographic pole. South of Earth's geographic pole corresponds to what? The north of Earth's magnetic field. North of what? Earth's magnetic pole. So this is very important, guys. Be careful, okay? What is magnetic fields? Magnetic fields, a region in which magnetic force could be measured. A region in which a magnetic force could be measured. So the magnetic field lines are invisible, okay? So we cannot see with our naked eye, but we can observe the Earth's we can observe the magnetic field lines by the filing papers, okay, like a piece of magnetic material. It's very tiny, like for example, this is north and this is south. The magnetic field usually comes out from the north pole. These lines, this is imaginary, so invisible. We cannot see these field lines, but the field lines usually comes out from the north pole and it goes to the south pole. Okay? The south pole can absorb the fields always. Okay? The south pole absorbs this field and the north pole, they take out field lines. This is from the outside of the magnetism. From the outside of the magnetism, how the magnetic field lines moves. You have to say from north to south, from outside of bar magnetism. What about inside magnetism? Inside the magnetism, the magnetic field lines moves from what? From south to north. Look, inside the magnetism, this feels like a circular loop. There is no ending point and starting point of the field lines. Be careful. We don't have ending point and starting point of the field lines of the magnetic field. They are in a circular loop, okay? Inside the magnetism, the field line is moves from south to north, but outside of magnetism from north to south. We have some notes about the magnetic field, and magnetic field measured in Tesla. The SI unit of magnetic field is what? Is Tesla. So its symbol is B. The magnetic field, B, what do you mean by this B? Capital B is the magnetic field, okay? This line is what? Magnetic field. A magnetic field is a vector quantity. Why magnetic field is a vector quantity? What do you mean by vector quantity in physics? A quantity that has both magnitude and direction, okay? In the magnetic field, we have both magnitude and direction. Measure it in Tesla. The amount of magnetic field is directly proportional to the magnetic field lines. More field lines, it means that the strong magnetism. Okay? So the less magnetic field lines, it means that this magnetism is weak magnetism. So the number of magnetic field lines determines the strong and the weak of magnetism, or tells us about the strongest and the weakness of the magnetism. Magnetic field lines appears to begin at north pole of magnet and to the south pole from the outside of magnetism. However, magnetic field lines have no beginning or ending point. Rather, they always form a closed loop. But outside of magnetism moves out from the north and goes to the south. but inside magnetism from south to north. The magnetic field is greater near the poles. Why? Why the magnetic field is great in the poles? Because in the poles, there is a lot of magnetic field lines in a small area. The magnetic field line is concentrated at the poles. So that is why the magnetic field is stronger in the pole than the other side. The magnetic field is greater near the poles because the number of magnetic field lines is concentrated at the poles. Magnetic force is a field force. If you remember in grade 11, chapter 3, section 1, we studied about the force. And we have two different types of force, contact force and non-contact force. The non-contact force sometimes is called the field force, a force that acting on the object without physical contact. Okay? So that is why the magnetic field or magnetic force is a field force without physical contact. The direction of the magnetic field at any location is defined as what? The direction that the north pole of the compass needle points to at that location. The compass always indicated the north pole for the magnetic field lines. What is compass? A device having a magnetic needles. Magnetic what? Magnetic needles that indicates the direction of the magnetic field. Compass is a device that has having a magnetic needle. This is the magnetic needle. This end is north and this end is south. So we can determine the magnetic field direction. Question 1 in chapter review and review assess. What are the minimum number of poles for magnet? 2 poles. Each magnet has 2 poles at least. Okay. When you break a magnet in half, when you break a magnet in what? In half. How many poles does each piece have? This is not add, this is half. If the question asks us to how many poles does each piece have, if the magnet break into half, you have to say 2 poles. Each piece have 2 poles. But if the question says how many, if you when you break a magnet in half or 2 pieces, how many poles does each piece add? If the question says add, you have to say 1 pole will be added to each piece. Drawing a line of a magnetic field using a compass. So this is very important, guys, to find the direction of the magnetic field. For example, assume that this figure, we have a bar magnet. This is north pole and this is south pole. The direction of the field lines, it will be like this. Okay? The north pole of the compass to always toward the south pole. Why? Because the north part, the field lines comes out from the north and to the south. Here, if you put the compass here, the needle of the compass is directed in the direction of the field lines. If you put the compass here, the direction of the field line, it will be like this. If you put another compass here, it is north pole always directed to what? To the south pole of the bar magnetism. If you put a small movable magnet compass in a magnetic field region, its needle will align itself in the direction of the lines of the magnetic field at all successive points. The direction of the magnetic field at any point is defined as the direction of the north pole of the magnet compass at the same point. You have 2 iron, question 3, you have 2 iron bars and a ball of string in your position. 1 iron bar is magnetized and 1 iron bar is not. Okay, we have 2 iron bar, identical iron bar. 1 iron bar is magnetized, the other is not. How can you determine which iron bar is magnetized? So this is very good question, guys. How can you determine which iron bar is magnetized? Okay, without approaching to the magnetic material. By suspending through the thread or the string. If we suspend both the iron bar and the magnetism into the air, hang each of the bars or suspend each of the bar by the string, the magnetized bar will align itself with the Earth's magnetic field. Okay, the magnetism will align with what? With the Earth's magnetic field. Why? Because in the Earth, at the surface of the Earth, there is a magnetic field. Okay? If you put a compass, if you put many or several compass, all compasses, needles, they directed into the same direction, and they will align with the direction of the magnetic field of the Earth's magnetic field. So the iron with the magnetized iron realign with what? With the Earth's magnetic field. But the non-magnetism, the iron bar with non-magnetism, when it's not magnetized, it doesn't realign. So the bar that is realigned with the Earth's magnetic field, we can say this bar is magnetized. The other, when it is not realigned with the Earth's magnetic field, this is not a magnetism. Question 4. Why does a very strong magnet attract both poles of the weak magnet? Because it realigns the domain of the weaker magnet. For example, if we have two magnetism, okay, so this magnetism is a strong magnetism. Strong magnetism. Why? Why this magnetism is strong magnetism? Because the domains and the electrons are directed into the same direction. As the domain gets the same direction, we can say this magnetism is a strong magnetism. But what do you mean by a weak magnetism? A weak magnetism, all domains is not in the same direction. Some of the domain is randomly. The domains are not in the same direction like this magnetism. So can we say this is a strong magnetism as well? No. This is weak magnetism. What is this? This is weak magnetism, okay? So the question, why does a very strong magnet attract both poles of a weak magnet? For example, if we bring this close to the this weak magnet into the strong magnetism, this strong magnetism can realign the randomly domains of this weak magnetism in the same direction. Okay? So the weak magnetism also becomes a strong magnetism. Why? Because the strong magnetism has effective on the weak magnetism. So this strong magnetism, they realign the randomly domains of the weak magnetism. So it makes all the domains in the same direction. Now both magnetism are a strong magnetism. Relation between magnetic flux and the magnetic field. So this is very important, guys. The students sometimes are struggling between the magnetic field and magnetic flux. So that is why they have a problem in chapter 6. In chapter 6, it's very important to distinguish between the magnetic field and the magnetic flux. Magnetic field, as we studied, assume that this is a bar magnetism. This is the field lines. This is field lines. The white line is represented for the magnetic field lines, which is invisible. We cannot see with our naked eye. This is the magnetic field lines. But what do you mean by flux? What is magnetic flux? It is symbol is phi. The number of field lines. Number of what? Field lines that cross what? A certain area. Cross what? Certain area at the right angle to that area and measure it by what? Weber or Tesla meter square. For example, if we have a specific area like circle or rectangle, no problem, okay? For example, if you put a conducting ring, okay? Conducting ring in the front of this magnetism, the number of the field lines that crossing this area, the area of this circle, okay? The number of the field lines that crosses this circle is called what? Flux. What is this lines? These lines are flux. What is the magnetic flux? Is the number of the magnetic field lines that cutting or crossing the certain area which is perpendicular to the magnetic field. Can we say this is flux? No, this is not flux. Why? Because this field line does not crossing the circle, the loop, the area. Which field becomes magnetic flux? The field is that crossing or cutting the certain area of the loop. So sometimes this loop may be, this area may be circle, rectangle, square. It depends. It doesn't matter. Okay? What is the magnetic flux? Once again, listen carefully. Magnetic flux is the number of field lines that cross what? A certain area. Measure it in what? Measure it in Tesla meter square or flux. Measure it in what? Tesla meter square or Weber. Look. Now we have an equation to find flux is equal to what? The area of the loop and the magnetic field lines which is crosses the loop at right angle. This is flux. What is flux? Is the number of lines that crosses the certain area which is perpendicular to the direction of the magnetic field. Flux is measured in what? Weber, sorry. Flux is measured in what? Measured in Weber. What is the equivalent unit of Weber? Magnetic field, Tesla. Area, meter square. Which of the following is correct to represent the unit of the magnetic flux? Weber or Tesla meter square? Both are correct. The SI unit of the flux is Weber. It is equivalent unit is equal to what? Tesla meter square. Phi is magnetic flux. B is magnetic field strength, measured in Tesla. Theta angle between magnetic field lines and the normal to the area. A is area vector. What is area vector? This is area vector. Area vector, a vector whose magnitude is the area of the loop, and direction is the normal to it. What is area vector? A vector whose magnitude is the area and direction is the normal to it. The SI unit of magnetic flux is Weber, which is equal to Tesla meter square. The larger value of the magnetic flux shows that the intensity of the magnetic field. Larger are the pole of the magnet. Magnetic field intensity, this is the intensity of the magnetic field. Flux is equal to what? AB, cosine theta. What about the magnetic field intensity? B is equal to what? Is equal to flux over A cosine theta. Okay? So Tesla is equal to Weber over meter square. Consider two identical loops placed normal to the axis of the magnet, one close to the pole of the magnet and the other close to its side. In which loop the more line will cross the loop? Absolutely in the poles. Why? Because in the pole, near the poles there is a lot of magnetic fields, and the magnetic field lines are concentrated in the pole, in the loop, in the poles. The loop that closes to the pole. Why? Because the large value of the magnetic flux shows that the intensity of the magnetic field is larger at the pole of the other magnetism. Magnetic flux has maximum value when the magnetic field lines are perpendicular to the plane of the loop. When does? Assume that this is magnetic field. Assume that this is magnetic field, okay? And for example, when does magnetic flux has maximum value? When the magnetic field lines are perpendicular to what? To the plane of the loop. When the plane of the loop is perpendicular, it means that area vector is parallel, okay? So for example, if the loop is perpendicular when the loop is perpendicular, so in this case the plane of the loop is perpendicular. This is plane of the loop. Okay, what is this? Plane of the loop. And this is area vector. What is this? This is area vector. Area vector with the magnetic field in this case is parallel to each other. Area vector is parallel to each other. Okay, in this case the area vector is parallel to each other. Okay, so the area vector and the magnetic field are in the same direction. The angle between them is what? In this case, theta is equal to what? 0. When theta is 0, flux is equal to what? A, B, cosine 0. Cosine 0, 1. 1 is maximum. Flux becomes what? Becomes max. When does magnetic flux has maximum value? When the plane of the loop is perpendicular or area vector is parallel. So what about if the plane of the loop is parallel? This is plane of the loop is parallel to the direction of the field. In that case, the direction of what? Of the magnetic, the area vector. The direction of the area vector is what? Is perpendicular to what? To the magnetic field. When plane of the loop is parallel to the direction of the field, the area vector is perpendicular. Angle between A and B is 90. Cosine 90, A, B, cosine 90 is equal to 0. Flux becomes what? Becomes 0. When does magnetic flux has 0 value? When the plane of the loop is parallel to the direction of the field, or its area vector is perpendicular to the direction of the magnetic field. So when does it between maximum and minimum value? When the plane of the loop is in tilted angle, not perpendicular, not parallel, like okay, like for example, when the plane of the loop is oriented in a tilted angle, this becomes area vector. Okay, area vector with the magnetic field is not perpendicular, not parallel between maximum and minimum value. So here we have some directions. This is north, upward, south, downward, east, west, into the page, out of the page. Into the page, represented by negative Z, out of the page, positive Z. Into the page sometimes can represent by the cross, out of the page like a dot. We will study in detail in the other sections. What is magnetic hysteresis? The last topic in this section. When a ferromagnetic material like a piece of soft iron is exposed to the magnetic field, okay, it becomes magnetized. The magnetic flux density is increased non-linearly, okay, with the increasing of the applied field. The relation between, guys, between the magnetic flux, okay, and the magnetic field lines is not directly, it's not linearly, okay, it is like a curve. So the magnetic hysteresis curve between what? The curve magnetic field and magnetic flux. We finished this section. Now we are going to solve the questions of the section review. Question 1, when a bar magnet is broken into two pieces, how many poles would each pole have? Each pole have 2 poles. Look at this question. Very good question, guys. So it has been brought in Wazari exam, this question. Look. When a bar magnet, question 2. Which of the compass needle orientation in the figure may correctly describe the magnetic field at the point? Guys, look. How many compasses do we have? We have 1, 2, 3, 4, 5, 6, 7. We have 7 compasses. This is north and this is south. if you remember, we studied the magnetic field lines usually comes out from the north and goes to the south. This is field lines. Sorry. Okay. This is the field lines. The field lines usually comes out from the north and goes to the south. Okay? Look, can we say the compass D is correct? No. This needle, it should be directed in this direction, not in this direction. D is incorrect. Compass C. The compass C at this point, the direction of the field, it should be in this direction, not upward. This is not correct. Compass B, it is the needle's direction is the same direction of the field that I drawn. Can we say B is correct? Yes. Compass A, they have the same direction that I drew from the north to the south. A also is correct. Compass F, it should be to the left, but here is directed to the right. F is also incorrect. Compass E, it should be directed also to the south, but here the needle is directed to the north. Also, this is incorrect. This is very good question. The correct answer, only compass A and compass B. So here we have some Wizari questions about section 1. So that's all about the section 1 in chapter 5, inshallah. In the next lesson, we will explain section 2 in chapter 5. Thank you for listening. Keep up your best doing. Have a good time.